Hello, in this video I'm going to solve the following problem for you, which is a problem on the topic of trigonometric numerical calculations. Prove the following identity. Sine theta times sine 60 degrees minus theta times sine 60 degrees plus theta equals to 4 times sine 3 theta. Prove a similar formula for cosine and then determine the exact value of the following product. Tangent of 12 degrees times tangent of 48 degrees times tangent of 54 degrees and finally times tangent of 72 degrees. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do the calculations correctly, the answer to the last part of the problem is 1. The interested student for similar videos can refer to the following playlist. The link to the PDF file that you can see on the display now is in the description below the video. Okay, now let us solve the first part of the problem. So we want to prove this identity. Okay, I can start opening this up using the subtraction and addition formula for sine. But if you don't mind, let me solve this in a general way. So I would say that, okay, is there any way that I can simplify this combination? Say sine A minus B multiplied by sine A plus B. Okay. I want to prove that this becomes equal, very similar to the conjugate rule. So it becomes sine of the first angle squared minus sine of the second angle squared. This is the first thing that I will show, and then use this to open up this part by giving the role of A to 60 degrees and giving the role of B to theta. Yes, so let us first prove this one. So I start from the left-hand side, and using the subtraction and addition formula, sine, I will open them up. So it becomes sine of the first one times cosine of the second one minus the other way around, sine of the second one, cosine of the first one. The second one is the same, but this will become positive, okay? So this becomes sine A, cosine B, and then plus sine B, cosine A. Okay, but if I want to multiply these two pairs of brackets, you see that this is the same number, this is the same number. Once they are subtracted, once they are added, and I am supposed to multiply them. So that's exactly the conjugate pattern. So the answer becomes the first one squared, which becomes sine squared A cosine B squared, minus the second one squared, so sine B squared times cosine A squared. But my goal is to prove this combination is equal to that, so it means that I only need to have sine in my expression. Okay, but here you see that I have one cosine of B that I don't need. I also have one cosine of A that I don't need. So I have to eliminate these two cosines in favor of sines. So what I will do, I will remind myself of the famous combination between sine and cosine. So I will copy and paste the first one. But for this one, I can write 1 minus sine B squared. And then minus sine B squared, I keep it because I need it for the right-hand side, but I don't need this cosine, so I eliminate it using this very famous formula. So cosine A squared is 1 minus sine A squared. And then I multiply this inside, so it becomes sine A squared minus sine A squared times sine B squared. And I multiply this in, so minus sine B squared plus sine B squared sine A squared. And then you immediately realize that these two terms are the same with opposite signs, so they are gone, and I am left exactly with what I need. So it becomes sine A squared minus sine b squared. And that is equal to the right-hand side. So that is a nice formula. Remembering it is also very easy because it's very similar to the conjugate rule. Of course, the proof goes from the conjugate rule. It's not exactly conjugate rule, but it's very similar. Anyway, now I go back to the main problem here, okay? So what I will do, I want to start from the left-hand side. Nothing I can do for this, so let me copy and paste this one. But this part is exactly that identity, as I told you before. Give the role of A to 60 degrees and give the role of B to theta, and this product becomes that, so I can use that identity. That identity tells me that the sine of the first one is squared, so I open a pair of brackets and write the answer of this here. It becomes sine of the first one, 60 degrees squared, minus sine of the second one squared. But of course, sine of 60 degrees is one of those famous, 60 degrees is one of those famous angles. So sine of 60 degrees is the square root of 3 over 2. So I copy and paste the first one. And then this is the square root of 3 over 2 to the power of 2. And then I copy and paste this one as well. Yes? Okay. But this number to power 2 is just 3/4, and then I have minus sine squared theta, and then I multiply this in. This 4 will cancel that 4, so I will get 3 sine theta minus 4 sine theta cubed. But it seems a little bit weird because I want to continue and reach to sine 3 theta. It is not that obvious how we can continue to reach to that part. Might be it's a good idea to start from the right-hand side and simplify it in a way that I can reach to this as well. Okay, so in other words, instead of going from the left-hand side directly to the right-hand side, I manipulated the left-hand side. I realized that the left-hand side is equal to this expression. Now I will start from the right-hand side with the hope that I can simplify the right-hand side and reach to the same expression. So what can I do? Of course, for some of you, depending in which country you're living, these formulas might be famous for you. But here, I want to prove it. Okay, so sine 3 theta, how can I do something with it? So let me write it immediately here. So sine 3 theta, I write it as sine 2 theta plus theta. Okay, because my goal is to write sine 3 theta in terms of sine theta only. Okay, and of course I can write sine theta plus theta plus theta. And the problem is that the formulas for addition and subtraction are only for the sine of the sum of two angles. Okay, so I will break it up into two angles. Okay, so 3 theta can be written as 2 theta plus theta. So then it becomes sine of the first one, cosine of the second one, plus sine of the second one, and cosine of the first one. But for sine 2 theta, we have a famous formula, so this becomes 2 sine theta, cosine theta. This is what I wrote for the first one. I also have another cosine theta here. I copy and paste the sine theta here. And the problem is that for cosine 2 theta, I have three formulas. One formula is a mixture between sine and cosine. One formula expresses cosine 2 theta solely in terms of cosine, and another formula expresses it solely in terms of sine. But because I want to have sine involved, I use the third alternative. So in principle, instead of that one, I would write 1 minus 2 sine theta squared. So I use this version of formula for cosine 2 theta. And then I open it up. Cosine is cosine squared. And then I multiply this in, so it becomes plus sine theta, and then minus 2 sine theta cubed. Okay? This is not wrong, but that is not exactly what I want. What I want is only expressed in terms of sine. But here, it's a mixture of sine and cosine, but this is again easy. I use the famous formula, so let me continue here. So let me continue here. So this becomes 2 sine theta, and then instead of that, I write 1 minus sine theta squared. This is what I wrote for this. And then I have a sine theta, and then I have minus 2 sine theta cubed. Yes? And then, of course, it is clear what to do. I just multiply this in, so it becomes 2 sine theta minus 2 sine theta cubed plus sine theta minus 2 sine theta cubed. And then immediately you see that these 2 sine theta plus another sine theta, it becomes 3 sine theta minus 2 sine theta cubed minus 2 sine theta cubed becomes minus 4 sine theta cubed. Okay? Now everything becomes clear, yes? Because when I opened up the left-hand side, I got that expression. When I opened up the right-hand side, I got exactly the same expression. Because the left-hand side and right-hand side are both equal to the same expression, from these two, I can conclude immediately that, of course, the left-hand side should be equal to the right-hand side. And the identity is proved. Okay, in the problem, it is mentioned to prove something similar for cosine. Now, of course, I don't know if the problem is designed in a nice way or not, but I hope that you can guess at least and then prove it. So I just write it for you, and then you can do it as an exercise for yourself. The formula similar for cosine will be very similar. Just change every sine to cosine. So it becomes 4 cosine theta, and then cosine 60 degrees minus theta, and then cosine 60 degrees plus theta. It becomes cosine 3 theta again. Okay, but of course, again, if you want to prove this is the formula that you're supposed to prove. I don't want to do it here because it's very similar, but this combination is not exactly as that. We have also a formula for this way for cosine. Cosine A minus B times cosine A plus B is similar to that one, but it becomes cosine of the first one squared, not minus cosine of the second one squared, minus sine of the second one squared. Or of course, if you want, you can write it the other way around. Depends which one you prefer. So you can also write it as cosine B squared and then minus sine A squared. This is also possible. So my recommendation is that, for example, use the same method to prove the first version of this identity, and then again give the role of A to 60 degrees, B to theta, and then open it up. And again, you will not be able to reach the cosine 3 theta immediately, but then you can use the same trick to open up cosine 3 theta. And if you use the same trick, meaning writing 3 theta as 2 theta plus theta, finally you should be able to get this formula. I'm sorry, cosine. Okay, and then in a similar way, this can be proven. So this part, I leave it to you to prove it, because it's it's very similar to the previous method. Okay, but of course, what is wanted in the problem is not related to sine, it's not related to cosine, it's related to tangent. Okay, but if you look at the angles, so if you see, usually even these kind of problems are common in mathematics. You solve one part of the problem, it's more or less without mentioning it directly, it is a guide to the second part or the third part of the problem, okay? So if I give the role of theta to 12, and then 60 minus 12 becomes 48, 60 plus theta becomes 72. So that's good. So if I can find a similar formula for tangent, then of course this multiplied by that, I will immediately be able to say something about it. Yeah, so that's the motive behind it. But first, I need a formula similar to this formula and that formula for tangent. But that is very easy to derive. Why? You can divide the sides of this equation by corresponding sides of this equation, by this identity. How? So I will take the left-hand side of this and then divide it by the left-hand side of this. So what happens? It becomes 4 sine theta sine 60 degrees minus theta sine 60 degrees plus theta. And I divide it by the left-hand side of the second identity that you're supposed to prove yourself. It becomes 4 cosine theta cosine 60 degrees minus theta and cosine 60 degrees plus theta. Yes? Of course, if I want to keep equality, when I divide the left-hand sides, I should also divide the right-hand sides. The right-hand side of the first one is this. The right-hand side of the second one is this. But now something interesting happens, yes? Because 4 and 4 are cancelled. Sine theta over cosine theta, because this can be written as 3 fractions multiplied. The first fraction multiplied by the second fraction multiplied by the third fraction. But the first fraction is just nothing except tangent theta. Sine of this angle divided by cosine of the same angle, it becomes tangent of that angle. And the same story here, it becomes tangent of 60 degrees plus theta. And on the right-hand side, I will have tangent of an angle, cosine of the same angle is tangent of that angle. So I was able to prove this identity using those identities. So the only difference is that for sine and cosine, we have a factor of 4, but the similar formula for tangent lacks the factor of 4. Okay, now because this is an identity, so it is valid for every choice of theta, including theta to be 12 degrees. So if I choose theta to be 12 degrees and put it here, it becomes tangent 12 degrees multiplied by tangent 60 degrees minus 12 degrees, which is 48 degrees, multiplied by tangent 60 degrees plus 12 degrees becomes 72 degrees. But then this should be equal to tangent of 3 times theta, which is 36 degrees. Okay? Because none of these angles are famous, so that was a very indirect way of proving that this product can be written compactly as tangent of 36 degrees. But why this is useful? Because my question mark is this one. So if you don't mind, let me write them in a different order. I want to keep them next to one another and then this separately. So the question mark is tangent 12 degrees times tangent 48 degrees times tangent 72 degrees. But my question mark also includes tangent 54 degrees. But for these 3, I can write tangent 36 degrees and then multiply it by tangent 54 degrees. But this is very simple to calculate, even though these angles are not famous angles, but we know that 36 degrees plus 54 degrees is 90 degrees. In other words, these angles are complementary. If the angles are complementary, the product of tangents is always equal to 1. And that is exactly what we wanted to show with this problem. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.